Howdy, I'm Gemma Goddard and welcome to my demonstration of my load balancer project. Today we will be understanding the project files and classes, reviewing inputs and how to run, running the project and understanding output, and assessing how different inputs impact results. We'll begin by understanding the project files and classes. As a brief overview, load balancing is a computing process that distributes tasks and network traffic across resources to improve efficiency and reliability of an application or service. It helps to avoid overloading some resources while leaving others idle to optimize response time and increase availability of applications for users. Let's start off by having a brief understanding of the classes and their purpose. The first class is the request class. This class serves like a struct and it entails basic information about each request, such as the IP address in, IP address out, and time to process. The next class is the web servers class. This class has a vector of requests that it is meant to process and a server ID. This class is where each of the requests will get processed, and the time is relative to the load balancer class that is passed in. The main driver of this class is the load balancer class. This class helps to manage and allocate or deallocate servers as requests come in. This class has a queue of requests that will be passed on to the different web servers based on different properties in the getNextServer function below. It also adds requests to the request queue that can be processed, and there's also IP validation to help ensure and prevent hacking. The main driver for optimal performance in allocating and deallocating requests is the getNextServer function. GetNextServer function first begins by looking to turn off any servers that are currently on but have a small load. This allows them to turn off and process requests that are currently in their request queue, but also not accept more because maybe some other server has the availability to load more. Then look to add a request to a web server that has availability and is not overperforming. And if we aren't able to find that, we look to allocate a new web server. And if that isn't a possibility, we then add the request to the server with the least number of requests currently. The process request function is also very important as it serves as the driver for increasing the time and managing time, as well as taking each of the incoming requests and figuring out which server it should go to and adding it to that server's request queue. One thing to additionally note is the IP validation function below. As mentioned above, anytime a request comes in, the IP address is validated to make sure that it's a good IP, and if not, the request will not be added to the queue to be processed. This is the driver class, and it has a bunch of helper functions to help instantiate and get the load balancer running. We have this function to fill the queue initially, and we also are able to randomly add requests here. That is done by a thread that just every however many milliseconds will add a random request. This helps to mimic the structure of the actual web. The rest of this class is really just initializing all the web servers and the load balancer, and then also calling the function to start. So we will be reviewing the project inputs and how to run it. Because of the makefile building, this project is very easy. And then to run it, you run ./balancer, and then the inputs for this program -s are the number of servers and -c are the number of clock cycles. Now this is the exciting part where we get to see the load balancer in action and see how it dynamically allocates and deallocates different web servers to process requests. To make this a little bit easier, we will be looking at a txt file that has all the program output. The thing to note is how the load balancer is assigning requests. We see that these first few requests are all being added to server 1 until we see server 2 turn on. This is because we had server 1 loading, however it reached the load and we didn't want it to perform too hard, so we then added another server. And we can see that as we continue to add requests. Now as we scroll to the part where most of the requests are being processed, you're able to see each server processing or whatever request this is. And this first part is the start time and this part is the end time globally. And as you can see here, this is the time to process the request and that is matched to that interval. You can also see within the output, requests are being randomly added, and then here you can see that this IP address was blocked, but here you can see it being added to the request queue and then the load balancer adding it to which server it best fits. Many of these processes will continue to load and process requests, but as we get to the end, when requests start slowing down, we can start to see that servers are starting to be deallocated. We got towards the end here, we can see that lots of servers are turning off because they are not performing at a high level, and so fewer web servers are able to process the remaining requests. And so as we see here, it's turning off all these servers, and then these servers continue to process what requests they have left, but then when we see here, whenever new requests come in, it will be added to one of the active servers only. At the end of this output, we are able to see the total number of requests that it started off with and the number of requests that ended in the queue. Also making note that there were 9 invalid IP addresses. Lastly, we will be doing a brief assessment of how if you change different input values, how that affects performance. Looking at different program inputs, of course there is a positive correlation between the number of servers and the number of requests processed as well as the time increased, but the main factor also has to do with this load variable that we are declaring when a server is either overloaded or full. Here I have run the program with different loads of 10, 50, 100, and 500, and we can see here that with the load of 10, we end up with 54. With 50, we end up with 62 requests left. With 100, we are left with 114 requests, and with 500, we're left with 814 requests left in the queue. It's because this is when we are defining what a overloaded server means, and so for lower load numbers, then more servers are going to be allocated quicker, so it's able to process more requests. However, here, with the load of 500, not as many servers are being allocated, so it's taking longer to load requests. It is important to find an easy medium because although the load of 10 processed the most requests, it also didn't turn off any of the servers, so we were running at full capacity the whole time, which could be very costly. Thank you for your time. I hope that you enjoyed learning about my load balancing project.